Hi guys, we're back for another chapter. I'm gonna try not to overload you this time. I'm gonna watch the clock. It's 7:45. I'm not gonna tell you what day it is, but I'll try to only make these 30 minutes. I know my previous videos were going a little long. Sorry about that. Just trying to get everything out there I can for you. I really hope they are taking advantage of this material because I know a lot of other professors that are not doing near this kind of work. I'm not saying that I'm going above and beyond, but I really am trying to make this work for y'all. I know it's unfortunate all the way around. If you're like me, I've been at home Saturday, Sunday, and today, and I've not been anywhere, and I am about to lose my mind. I might even come out of this thing divorced. I'm just kidding, but really, it's getting real over here. So, I do also my unsolicited advice for you. Please stay at home and practice social distancing so we can kick this thing in the butt and get our lives back to normal. Okay, it is real. I know some of us think that we're invincible and it won't hurt us or it won't get us. It's just going to get all these other Americans, not us. But it is, and it will, and it doesn't discriminate. Healthy, unhealthy, it doesn't care. So, y'all do y'all's part and let's flatten the curve and stop the spread. All right, now that I've wasted 3 minutes. All right, chapter 16, acids and bases. Um, the first part of this chapter is Batman and Black Mask. I'm not going to read that to you, but I strongly encourage you to go read it. It's really cute. Sorry, that was a fun word, huh? It's on page 685 in your text. And remember, oh my gosh, y'all. My writing has gotten terrible. Let me redo that. Remember, if you did not take your book with you on spring break and you live a long distance from Clinton, I did send y'all the instructions on how to go about accessing your book online 100% free. I'm pretty certain I did that. If I did not, somebody shoot me an email and I can do that as soon as possible. But that's a great thing that all these publishers are doing in this desperate time. All right, so 685, you can find the story of Batman and Black Mask. Go read that. I will pull maybe a quiz or test question from that, so be sure you go read that, okay? All right, 16.2, the nature of acids and bases. All right, general properties of acids are they have a sour taste. Vinegar is sour due to acetic acid. Citrus fruits have that twang due to citric acid. Acids react with certain metals to produce hydrogen gas. In other words, if y'all might know this from some reactions we've done, I think it was in Chem 1, where we put the copper and zinc in sulfuric acid and we attached the electrodes to it, and the copper came off in the solution and turned the solution blue. Acids will eventually completely dissolve any metal or most metals. Okay, then a big thing we learned in the group 1 cation lab is that acids, we test that with blue litmus paper. That blue litmus paper turns red if our solution is acidic. Okay, so those are the general properties of acids. General property of bases, they have a bitter taste. Alkaloids, this is a side note. Someone told me that I needed to try alkaline water. And I'm really interested in this. Oh my gosh, do y'all hear my dogs? If it's not the dogs, it's the cats. You know, just trying to make the best of it. Anyway, back to bases. Bases are slippery to touch. So I don't know if you have ever got NaOH on your hands in the lab, but it makes your fingers very slippery. It should not be on your fingers unless it is a very, very dilute solution. Bases. We use red litmus paper to test for basicity. There, I got it. Oh my gosh. And red litmus paper turns blue. Sorry about all the distractions I have going on in the background. I want to holler at them, but I think that will be very tacky on video. All right. Carry on, Shelby. Carry on. Oh crap, that's not what I wanted to do. I wanted to scroll. Oh no. Oh no, I'm still learning. Okay. All right, so definitions of acids and bases. I might have to slide this down some. All right. Each of these definitions has limits, and no single definition is correct. There are 3 definitions of acids and bases that we will talk about. The first 2 listed here. All right, the Arrhenius definition is the simplest and most restrictive. So in terms of the Arrhenius definition, an acid is a substance that when dissolved in water produces a hydrogen ion. Note that the hydrogen ion can exist in water. Cannot read, Shelby, exist in water. Instead, it reacts with water molecules to produce a hydronium ion. And therefore, in this chapter, we will use H plus and H3O plus interchangeably. Basically, that's just protonated water. If a hydrogen ion is in water, it's going to form the hydronium ion. Let me see. This is what it, oh gosh, I want to annotate. Okay, I guess I just have to do it this way. So this is what it would look like. Sorry, guys. All right, so that's what the hydronium ion looks like. We just have this added hydrogen on it. According to the Arrhenius definition, a base is a substance that when dissolved in water produces a hydroxide ion. So let's look at an example of each. I'm gonna do the acid, then I'm gonna erase it, then we'll do the base. So acid would be like HCl, that was aqueous. Well, in water, it exists as H plus, Cl minus. That's an acid. Let me clear. Base, on the other hand, example is sodium hydroxide. When dissolved in water, it exists as Na plus and OH minus. So produces that OH, so therefore it is considered a base. I'll show you another example of both of those in just a second. All right, I'm gonna go ahead and clear this. No, clear that too. All right, so those were Arrhenius acid bases. The next are Bronsted-Lowry, and this is the more widely acceptable definition of acids and bases. So, let me do this real quick. All right, so Bronsted-Lowry focuses more on the transfer of a hydrogen ion, so an H plus ion. Since H plus ion is a proton, like literally that is all it is a proton. Without its electrons, the definition focuses on the idea of proton donor and proton acceptor. So, according to the Bronsted-Lowry definition, an acid is a proton donor. So in order for it to be a proton donor, it has to have an ionizable hydrogen. What that means is when it's dissolved in an aqueous solution, that hydrogen has to come off, and that's how it exists as a proton donor. A base is a proton acceptor. So this must be an atom with an unshared pair of electrons, or a lone pair, so that it has room to bind that proton or that hydrogen ion. All Arrhenius acids and bases are also Bronsted-Lowry acids and bases, but not all Bronsted-Lowry acids and bases are Arrhenius acid bases, okay? So that seems confusing. Basically, Bronsted-Lowry definition, it includes the Arrhenius acids, but it branches the word acid and bases to more compounds. And I'll show you that in just a minute. I'll show you right now. All right, so with the Bronsted-Lowry definition, we have conjugate acid-base pairs. So first, before we do an example, this is very important, and I ask this all the time on test. No one seems to ever remember. Water and many other species that we'll come in contact with can act as an acid or a base. It depends on what it is in solution with. When something can act as an acid or a base, we say that it is amphoteric. Okay, so star this something. Do not forget this, because it will come up somewhere along the way. All right, so let's do an example. We'll do two. Let's look at an example of a Bronsted-Lowry acid, and we're also going to look at its conjugate base. So we'll take the Lewis acid we talked about. Okay, HCl and water. I really don't even have to include the water in the reaction because I say that HCl is aqueous, so it's understood that it's in the water. All right, well, what happens is the hydrogen is donated to water. So I form the hydronium ion. That's aqueous. And then I'm left with just the Cl minus ion. So that is your definition of a Bronsted-Lowry acid. It donates a hydrogen. It donated that hydrogen to water. All right, so in this example, HCl is your acid because it's donating a hydrogen. Water is your base because it is accepting your hydrogen. So then if I looked at their conjugate acid-base pairs, water here would be a conjugate acid of H2O, which is its base. It's conjugate acid and then its base. This is a conjugate acid because it has this extra hydrogen that it can then go on and donate. I am about to really hurt some dogs. All right, so then this Cl minus is a conjugate base of the acid HCl. Okay, so that's how conjugate acid-base pairs work. All right, let me clear this. Let's do another example. All right, let's look at a base this time. I really want to holler. So I'm about to. Give me a minute. Hush! Okay. Maybe, I don't know if you heard it or not. All right, another example. NH3. NH2O. I swear I've gotten worse at writing now. All right. So what happens here is NH3 is actually a base. So it accepts a hydrogen from water and forms the ammonium ion, thus leaving water as just OH. So NH3 is a Bronsted-Lowry base because it accepts a hydrogen. It is also a Lewis base because when dissolved in water, it forms an OH. So that's what I mean by a Bronsted-Lowry can also be an Arrhenius acid or base, but the reverse is not ever true. All right, so let's list our conjugate acid-base pairs. So NH3 is a base because I look on the opposite side of the equation and I see that it has accepted a hydrogen. So that would make water an acid because it gave up a hydrogen. I'm sorry, y'all. So NH4 then would be the conjugate acid of my base. And then OH would be the conjugate base of my acid. Because now it can accept a hydrogen because it has a lone pair on that oxygen. And NH4 can give up a hydrogen. Okay. All right, so let's look at example 16.1 down here. In each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, and the conjugate acid and the conjugate base. All right, so in order to just see what they're doing, we need to look at both sides of the reaction. So here, C5H5N, from the product side, it accepted a hydrogen ion. So this is my base. This has to be its conjugate acid. So then the same, I look at water. What does it do over here? It loses a hydrogen. So this is my acid. This is my conjugate base. Okay. And then we can look at this letter B. Again, I'm going to look what HNO3 is doing on the reactant side versus product side. So HNO3 lost a hydrogen, so it's an acid, and NO3 is its conjugate base. Then water here gained a hydrogen, so it's a base. This is its conjugate acid. So both of these examples and examples and the two I showed shows you how water can act as either an acid or a base. It can either accept a hydrogen or it can donate a hydrogen. All right, I believe I've been going about 20 minutes, so we're going to stop there. So this will be chapter 16, part 1. Hopefully it will not be another 12 parts, but it probably will. So y'all get ready. All right, see y'all soon.